For almost a century, we've known that most of our universe is, well, missing. We call it dark matter. But what if we've been thinking about it all wrong? What if it's not some kind of substance at all, but the actual shape of space-time? Or, even stranger, what if it's a structured, cosmic-scale atom? Let's dive into these two wild and, believe it or not, surprisingly connected ideas.
This right here is the question that's shaking up cosmology. For decades, we've been on this massive hunt for a mysterious particle, a WIMP, a weakly interacting massive particle that was supposed to solve everything. But we've found absolutely nothing. So, scientists are starting to ask a much bigger question. Are we even on the right track?
And look, this isn't just a hunch. Our standard model of the universe, the one we call lambda CDM, is really starting to show some serious cracks. There are two major observational problems that just won't go away, and they suggest our most basic assumptions might just be wrong. Okay, so let's take a closer look at these cracks. These are the anomalies out there in the real universe that are forcing us to completely rethink the cosmic dark side. First up is something called the cusp core problem. Our standard model predicts that dark matter should clump together, forming a super sharp, infinitely dense cusp right at the heart of galaxies. But when we actually point our telescopes at them, we see the exact opposite, a flat, stable core of constant density. The theory and the real world just don't line up. And the second crack? Well, that comes from the incredible James Webb Space Telescope. It's been finding these huge, fully formed, mature galaxies way back in the universe's infancy. According to our models, which depend on galaxies being built slowly from the bottom up through mergers, these things simply shouldn't exist that early. They formed way too fast.
So, faced with these huge problems, a pretty radical new idea has popped up. Maybe the answer isn't a new particle at all, but a whole new understanding of geometry itself.
This is the Cauchy-Ricci metric. Now, that's a bit of a mouthful, but the core idea is really elegant. It says that what we call dark matter is just the effect of space-time being warped in a very specific, beautiful way. Stars are following those weird flat rotation curves, not because of some invisible matter, but because they're just driving along the natural curved highways of the cosmos.
What's truly beautiful about this model is how simple it is. It solves the problem without inventing any new fundamental particles. It's a solution that just uses the general relativity we already know and love, but just applies it in a brand new way. So how does it work? Well, in essence, the theory suggests that spacetime's curvature follows this specific smooth curve. Mathematically, this creates the exact conditions needed to explain why galaxies spin the way they do. It even explains the flat core by proposing a kind of outward pressure that stops everything from collapsing. And it neatly trims the edges of the dark matter halo with the gravity from the surrounding galaxy cluster. It's a very neat package.
But there's another equally powerful theory that takes the complete opposite approach. It says dark matter is a particle. Actually, it's a whole family of them, and they form a structure that looks surprisingly familiar.
Say hello to the dual-component dark sector model, or DCDS. Forget about some random cloud of particles. This theory imagines that every single galaxy is built around a giant dark atom, a super-dense nucleus right at the center, with lighter particles orbiting it in distinct, quantized shells, kind of like an onion. The structure basically works like this. You've got heavy, dark quarks that form the nucleus, a bit like how our own strong force works. Then, lighter, dark leptons settle into these stable orbits, just like electrons around an atom. And any leftovers? They form a massive cosmic lattice of filaments that connect all these dark atoms together, acting like a conduction band for matter to flow between galaxies. So how does this actually build a better model? Let's just break it down. Instead of those slow mergers, you get rapid nucleus-first formation. That solves the JWST problem right there. And instead of a pointy cusp, you get a stable core, thanks to a repulsive dark force. It basically transforms the cosmic web from a random tangled mess into a structured, solid-state lattice.
So we have these two rival theories. One is all about smooth, elegant geometry, and the other is about lumpy, structured particles. I mean, they couldn't be more different, right? Well, this is where the story takes a really fascinating turn.
This is just incredible. In a stunning case of what you might call cosmic coincidence, both teams, working from completely opposite ends of the problem, discovered they needed the exact same mathematical ingredient to make their models work, something called a logarithmic potential. That's just a specific mathematical way of describing a gravitational field that perfectly explains why galaxies have those flat rotation curves.
So here's the crucial point. They might actually be two sides of the same coin. The smooth geometry of that Cauchy-Ritchie model could just be the large-scale, zoomed-out effect of the lumpy, quantized DCDS particles. The geometry is the field, and the particles are the little physical bits that actually create it.
So this leads us to the ultimate question. If one model is the zoomed-out view and the other is the zoomed-in view, how can we possibly test it? How do we figure out if the universe's foundation is fundamentally smooth or lumpy?
Luckily, we have a tool. We have a way to get the answer. It's a snapshot of the universe in its infancy, and it holds the clues we need to distinguish between these two incredible ideas.
That tool is the cosmic microwave background. This faint glow left over from the Big Bang acts like a backlight for the entire cosmos. By seeing how its light gets bent and distorted on its long journey to us, we can map the underlying structure of the universe with incredible precision. And here's the first test. If the smooth geometric Cauchy model is right, the CMB's power spectrum will show a smooth, broad lensing signal. But if the lumpy particle-based DCDS model is right, those discrete shells of dark matter will create oscillations, a distinct ringing effect at very specific scales, basically marking the exact radii of the dark atom's orbits.
The second test is even more direct, and I think it's even cooler. If we watch the light from a distant quasar pass through one of these DCDS galaxies, its magnification shouldn't be smooth. Instead, we should actually see it jump up in discrete steps, like a staircase, as the light passes through each successive dark lepton shell. A smooth geometric model? That would just produce a continuous, smooth slide. So, if these tests show a staircase, if they show that ringing pattern, the implications are just profound. It would mean our universe isn't some kind of fluid, but something far more structured, more rigid.
This quote from the source material just captures the paradigm shift perfectly. We would have to abandon this old idea of a passive dark fluid and accept that the cosmos is actually built on a rigid, organized scaffold, a crystal-like structure on the grandest scale you can possibly imagine. And that leaves us with one final, absolutely tantalizing thought. For years, cosmologists have been baffled by this thing called the axis of evil, which is a strange, unexplained alignment in the cosmic microwave background. If this DCDS model is correct, could this huge anomaly simply be us observing the primary orientation, the grain, of the entire cosmic lattice? The answer to that could literally change our view of reality itself.